When it comes, okay, to intermolecular bonding, okay, so we can have intermolecular bonding. Okay, intermolecular bonding, okay, is also going to be named as, okay, van der Waals forces of attraction. Now, these van der Waals forces of attraction, okay, you have three main type of intermolecular forces, yeah, which is going to be, one is hydrogen bonding. Second is going to be PD first, yeah, PD, and then you have ID. Okay, so when we look at this hydrogen bonding and the PD, okay, PD stands for permanent dipole, yeah. So hydrogen bonding and permanent dipole, okay, what is going to be the similarity with them? The similarity is going to be related to electronegativity, okay, which is going to be electronegativity is going to be affecting a lot, okay, when it comes to hydrogen bonding and PD, okay, because, okay, we are going to look into polar molecules, okay, polar molecules. As you know, okay, what is electronegativity? Electronegativity is going to be the ability, okay, of the atom to attract bonding pair of electron to itself. And polar molecules, okay, happen, okay, we have polarity, okay, whenever if you have a molecule, okay, and then there is going to be uneven distribution of electrons. At any point of time, okay, let's say, for example, if you have HCl, Cl is more electronegative, they will actually pull the electron closer to that side, making a lot of electron over here, less electron over here, and that is going to make delta negative, and this is going to be delta positive. So when you have this, and this condition is permanent, yeah, when you have this, and then I paste over here, this will create this a type of intermolecular bonding, okay, between delta negative and delta positive, which we call it as PD, permanent dipole, which is quite strong, okay. But when it comes to hydrogen bonding, okay, hydrogen bonding is going to be a special type of PD because it involves hydrogen, okay, being bonded to NOF, nitrogen, oxygen, and fluorine. Okay, because this nitrogen, oxygen, and fluorine, they are considered to be the most electronegative element in the periodic table. Okay, the bond that involves this ammonia, like for example, nitrogen, hydrogen, oxygen, hydrogen, and F. Okay, the bond, like for example, if you have, okay, water molecule. Okay, water molecule. Okay, I will actually draw something like this. This is water molecule. Ammonia. Okay, this is going to be, okay, let's say for now, I will draw like this. Okay. Okay, if I remove this, okay, this is ammonia, and I'm just going to put like this, okay, and then if you have HF, okay, HF will have, okay, this one, something like this. Okay, now I am just drawing, okay, with this thing because to make it easier for us to visualize the lone pair of electrons. Now do remember, okay, that, okay, this, okay, with another molecule is the one that is going to give you hydrogen bonding, yeah. So not, okay, not the, okay, sometimes students get confused. Hydrogen bonding happens within themselves. Okay, between this hydrogen, okay, they think that between this hydrogen and oxygen, this is hydrogen bonding. Wrong, yeah, it's not like that. Okay, so if you look over here, okay, we know that this part is delta negative, this part is delta negative, and this is delta positive, this is delta positive. Now, if you put it over here, okay, if you just put the number of delta positive and delta negative, you can see that the number of delta positive in one molecule of water is 2, and in one molecule of water is going to be 2 delta negative. It means that, okay, they can form, okay, like for example, 2 boys and 2 girls. You can have total of 2 couples. Yeah, 2 couples. So in this case, if you look over here, there is going to be 1 couple. Okay, if I just put delta negative, delta negative, delta positive, delta positive, 1 couple will be forming between here and here, delta negative and delta positive. Another couple can be formed here to here. Okay. And do remember, okay, if I have another 1 more molecule of this, okay, if I just draw, okay, and then I copy over here, I put it here, okay. And what happens, okay, there is going to be another bond over here, another bond over here. Okay, now this thing will continue with another molecule on top. Okay, it will continue with another molecule below. But what I want you to see is for that one particular molecule. Yeah, if I circle that one particular molecule here of water, you can see that, okay, there is going to be some sort of, okay, how many hydrogen bonding? Yeah, some sort of 1, 2, 3, and 4 hydrogen bonding. Okay, but what I want you to remember is because it's supposed to be only 2 couples. Yeah, okay, 2 couples. What happens is, okay, this hydrogen bonding over here belongs to this molecule. This hydrogen bonding over here belongs to this molecule, but this hydrogen bonding now does not belong to this molecule. It belongs to this molecule. This hydrogen bonding over here does not belong to this molecule. It belongs to this molecule. It means that, okay, water can on average, okay, form total of 2 hydrogen bonding per molecule. Okay, this is very important. Now, let's have a look at, okay, the similar example. If you quite difficult to visualize, I can understand. Okay, let's actually look the same example and we explore further here. Yeah. Now, if you explore the same example over here, okay, if you have ammonia, okay, what I'm going to do, okay, this is lone pair. Okay, and we know this one is going, rather than saying lone pair, okay, let's actually put it delta negative, delta positive, delta positive, delta positive. Yep. So all these are hydrogen. Okay, hydrogen. Now, how many delta negative I have per molecule? 1. How many delta positive per molecule that I have? I have total 3. Okay, you can see 1, 2, 3. It means that you have 1 boy, okay, and you have total of 3 girls. Okay, even though you have 3 girls, okay, they can be only 1 couple, boy and girl. Okay, so it means what will happen? Okay, it means that maybe this guy will get coupled up with this girl, and these 2 girls, okay, will go to waste. Yeah, basically they do not actually end up getting coupled. Yeah, it means that only 1 pair. Okay, so it means that if I represent this in form of drawing, yeah, this is delta negative. I'll just put it over here. Delta negative, delta positive, delta positive, delta positive. This guy will couple up with this. Okay. And, okay, what happens? This end up to go to waste. Okay. And if you draw again, okay, I will just simply draw nitrogen dot, okay, okay, hydrogen, hydrogen, hydrogen. This is going to actually form another 1 more to here. Okay, and the same thing. Okay, if you have another, it will bond to another thing. Okay, what we need to take note is every 2 delta plus will go to waste. Okay, this is delta plus, it will go to waste. Okay, this one will continue to bond. So if I just look at one particular molecule of ammonia, okay, when I just look at one particular ammonia, it will look as though there is one hydrogen bonding, and it will look as though I have two hydrogen bonding, okay, in that particular molecule, okay. But also similar like what I said, okay, that one hydrogen bonding belongs to this molecule, but this hydrogen bonding, it belongs to this molecule, not, okay, the other molecule. Okay, for ammonia, therefore, okay, it's going to be one hydrogen bonding, not two. Okay, is that clear, Ishana? Not clear? Okay, please repeat and watch again. Yeah, Jonathan, is that clear? Okay, now I will actually show you for HF. Yeah, HF. So you see here, this is delta plus, delta minus, delta minus, delta minus. If I copy this, maybe I'll just bring it over here first. Okay. Then if I copy this, okay, and I put it over here. Now, if you look over here, same thing, okay, if I put the delta plus and delta negative per molecule, how many delta plus, how many delta negative? You see one delta plus, okay, which is going to be one, okay, and how many delta negative? You have three. Similar like just now, okay, 1 and 3, yeah. But now, okay, if you have, okay, this one is like 1 and 3 delta, so similar like just now, I can just simply use the same example. You can have something like this, okay, I'll just draw, no problem. Okay, if you have one person, one guy, okay, again, you have three girls, okay, so only this and this will couple up, okay, and okay, the remaining two will go to waste. Okay, it will go to waste. So if I represent in form of here, okay, you can see delta minus delta H, one of them will couple up. Okay, this will go to waste, this will go to waste. Okay, and this another molecule, okay, let's say I copy this and I put it here. They will couple up here, okay. And if I just circle this one entire molecule, it will look as though one hydrogen bonding, another hydrogen bonding, okay. But this one hydrogen bonding, yes, belongs to this HF, but this hydrogen bonding actually belongs to this particular molecule. Okay, so in this case, there is going to be one hydrogen bonding per molecule of HF. Okay. In summary, okay, what I'm trying to say over here is, okay, when it comes to hydrogen bonding, I'll bring it over here. When it comes to hydrogen bonding, water, ammonia, and HF, okay, on average, each one molecule of water, okay, they will form, okay, you can just recall again, okay, if you have delta negative, delta positive, delta negative, delta positive, delta negative, delta positive, you have two lone pair here, so two delta plus. You have one lone pair, okay, and then three hydrogen and put over there. And this one for fluorine, you have three, and this is one. Okay, in total, if you have one, must be with one. Okay, so one hydrogen bonding per molecule. If you have one, must join with another one, so one hydrogen bonding per molecule. The remaining two will go to waste. The remaining two will go to waste. Okay, and you are going to have, okay, this one, okay, two boys, they are going to have total two hydrogen bonding per molecule. Okay, why we are learning about this? Okay, we generally, when we look at, okay, hydrogen bonding, okay, when we look at hydrogen bonding, if let's say, okay, if you look at group 17, okay, group 17, okay, we have, okay, FCBI, okay, and let's say I'm going to include hydrogen in front, okay, so all this. And, okay, we know that, okay, if I want to actually draw the graph for boiling point, okay, boiling point for these three molecules, what I will notice over here is, first thing, yeah, hydrogen HF, okay, HF, they have hydrogen bonding. Okay, HF, they have hydrogen bonding. The graph, okay, the boiling point will be very high for HF. Okay, the boiling point will be very high for HF. But when you look at HCl, HBr, and HI, they are all, okay, polar molecules. Okay, and how do I know whether they are polar or not? The previous lesson, yeah. Okay, Cl is more electronegative than hydrogen, Br is more electronegative, okay, I is more electronegative, okay. The arrangement of the electron, they are not, okay, symmetrical, they are polar molecules. If they are polar, I told you, if they are polar molecules, it's either can be hydrogen bonding or PD-PD. Okay, and in this case, hydrogen bonding only for NOF. Okay, so this is hydrogen bonding. Okay, but this one will be PD-PD. Okay, all these will be PD-PD. So I just copy, I'll just put it over here, permanent dipole. That will actually influence their boiling point. Now, what is extra thing that you need to know is this, okay? Cl, okay, the size, you see, H is same size, okay? Fluorine, okay, they are going to be smaller. As you go down the group, okay, group 17, the size supposed to increase, more number of shells. Okay, I hope you remember this. Okay, more number of shells, the size is increasing. Now, when the size is increasing, one is more number of shells. Why we have more number of shells? Because they have more electrons. Okay. If you have more electrons, okay, it means that you might have more delta negative, delta positive. It means, okay, they have delta negative, delta positive. It means that the delta negative over here is going to be stronger. Okay, it's going to be stronger compared to this delta negative. Okay, and it means that HI and HI, they can form stronger intermolecular bonding compared to HCl and HCl. Okay, so what does it mean? It means, okay, HF is already very strong, which is going to be hydrogen bonding. But how about HCl? HCl will be lower because they are going to be PD-PD. Okay, PD-PD. But as they move, okay, to HBr, it's supposed to go up. Why it's supposed to go up? I already told you, more number of electrons. It means that the delta negative and delta positive is going to be stronger. It means that van der Waals forces includes hydrogen bonding, PD-PD, and ID-ID. But in now, okay, we actually have, okay, Vivian. Now we have more electrons, okay, therefore, okay, the boiling point will actually increase. So you will have, okay, the HI will go up, but it will not go up until, okay, it overcomes HF. Okay, the boiling point of HF is still going to be high. So the graph will look like this. Okay, that is the explanation. Okay, for hydrogen bonding and PD-PD. Yeah. Now, if you look at, okay, the other graphs, okay, I will actually bring the graph over here. I'll copy this. If I put this over here, Now, what you can see over here is going to be a graph, okay, that extends, like for example, just now, okay, I show you the graph for between HF, HCl, HBr, and HI, which is going to be, let's see. Okay, if I put it over here, don't know whether you can really see or not. Yeah. So can you see here HF and then HCl, okay, and then HBr and HI. Can you see the graph? The same thing that like what we have discussed earlier. Okay, going down. Okay, because hydrogen bonding, then go up. Now, from this graph, I also want to explain few things. Okay, can you see here H2O, HF, and NH3? Okay, just now, Jonathan, Kevin, can you tell me on average how many hydrogen bonding that H2O can form? Can forget very fast. Yeah. Two, yeah. So if you look over here, on average they can form two, on average they can form one, on average they can form one. Now let's say I just draw separately here, boiling point, okay, of this HF, okay, H2O, ammonia. Okay, I want to draw them separately. Now, we know that according to this Pauling scale, yeah, I told you NOF, yeah, F is going to be the most electronegative element in your periodic table, yeah. So we know that, of course, okay, when hydrogen bonded to this, F should be the greater boiling point, HF. So let's say, for example, if I just randomly just say, okay, this is going to be the boiling point of HF. We expect HF to be like that, okay? And followed by O, which is going to be water, and followed by the lowest one, which is going to be ammonia. Because why? Electronegativity, yeah? So we know that this is going to be the most electronegative. Of course, the hydrogen bonding, we think that that is going to be the boiling point should be greater, stronger hydrogen bonding, okay? Now, in reality, it doesn't happen that way because if you have one hydrogen bonding, it will follow like this. Okay, I'll just show you in form of numbers so that you can understand better. Yeah. Now, let's say, for example, if you have only one, yeah, one hydrogen bonding, I give you a number, yeah, maybe 20. Okay, 20 for ammonia. Oxygen, maybe 40 for oxygen. Okay, for water. And then maybe 60. It means generally it is increasing and getting stronger. For example, I'm just giving a value. Yeah. But all these are for one hydrogen bonding. But we know this one has one hydrogen bonding. HF has one hydrogen bonding, but oxygen, they have two hydrogen bonding. So it's not 40. It should be 80. If you put 80, what happens? Automatically, oxygen will come in front of F. It means that I just need to erase this part and put H2O here. Cannot be there. Why? Because of the two hydrogen bond per molecule. Okay, that is the reason. But now you compare now. Can you see they are higher? Supposed to be ammonia. Okay, and supposed to be here should be water, but water went up. Why? Because on average, water forms two hydrogen bonding per molecule. Yeah, they will ask you to explain. Yeah. Now that is done, okay? But how about the others? You see, all these, okay, no problem, because why? Okay, all these are going to be polar molecules, polar molecules, polar molecules. And because of the size is increasing, they will just go up. Okay, similar like what we have learned. But there is one abnormality, anomalous value over here, yeah? Okay, it's not anomalous value. You can see all of them follow the trend, which is going to be going down, going up, going down, going up, going down, going up. But this one is keep on going up. Okay, can you tell me why? Walders, why they keep on going up?
To be honest, I'm not too sure.
Is this polar or non-polar? CH4.
Non-polar.
Non-polar. Okay. All these are non-polar. Okay, and we know the size is getting bigger and bigger. It means I told you when the size is getting bigger and bigger, electron is more stronger attraction, yeah, intermolecular forces. So it is understood why it's going up. But okay, when it comes to non-polar, okay, what kind of intermolecular bonding that we are talking about? Okay, the intermolecular bonding that we are talking about is ID-ID. Okay, ID-ID is the weakest intermolecular forces of attraction. Okay, and previously we are talking about hydrogen bonding. Hydrogen bonding. This is ID-ID. Of course, it is going to be weaker. Okay, CH4. Okay, the boiling point will be smaller because they are only going to be instantaneous dipole induced dipole. Yeah. So now, okay, coming back to here. Okay, when we look at ID-ID, okay, is not only for non-polar molecules. It is important to take note that it is for both polar and also non-polar molecules. But okay, non-polar molecules only have ID-ID. Okay, polar molecules, they can have hydrogen bonding if they have hydrogen and OF. And if they don't have that, then they only have PD-PD. Okay, so permanent dipole, okay. So doesn't matter whether it's ammonium, okay, having hydrogen bonding, doesn't matter it's going to be ACl, PD-PD. Both ammonia and ACl will definitely have ID-ID. But the strength, okay, in comparison, okay, to hydrogen bonding and PD-PD is too low, okay, it's not significant. Okay, so if they say what is the boiling point is very high for ammonia, what is actually the intermolecular forces of attraction, okay, that cause this? Then it's hydrogen bonding. We are not going to tell ID-ID, yeah, even though they have. Yeah. What is going to be the forces of attraction that causes a high boiling point for ACl, for example? We are going to talk about PD-PD. We are not going to talk about ID-ID. Yeah, but it is important to know that ID-ID focus for both. Okay, but when it comes to non-polar, there is no other option. It's always ID-ID. Example of non-polar molecules that have ID-ID. Yeah, generally non-polar molecules, Cl2. Okay. They are going to have ID-ID. So generally, okay, what do we actually see for, okay, now it's 2:30, yeah? We're supposed to end already, yeah? Am I correct? Sorry,
So
guys.
it was 15 minutes ago.
Yeah, sorry. It's my mistake. Okay, can I just finish this part, yeah? Okay, now, if you need to go, please go. Okay, it's being recorded. Okay, I will pass you. Yeah, but those who want to stay, please stay. Yeah, I'm going to finish. Now, if you have Cl, okay, Cl2, okay, this one molecule of Cl, okay, and when you have another molecule of Cl, okay, What happens, okay, because the electrons are dispersed, okay, the electrons can, at any instant, you can have more electrons compared to one side, okay, you can have, okay, this delta negative and delta positive at that instant. So we call it as instantaneous, okay, instantaneous dipole. Okay, there is a dipole, a polarity. And this is dipole is going to induce, if you have positive, it means a lot of negative will come over here. A lot of electrons will come. They will be attracted towards positive. And you will have less electron over here. This is going to induce, okay, induce another polarity in the next Cl2. So that is going to make this to become delta positive. This is going to be delta positive, delta negative and delta positive. There will be forces of attraction, which is a temporary forces of attraction, what we call as ID. Okay, so this is induced dipole, induced by the previous molecule. So that's why we call it instantaneous dipole, induced dipole, ID. And this is temporary. If it is temporary, it means at that particular instant, it keep on breaking and forming again. So it is the weakest, okay, weakest van der Waals forces or weakest intermolecular forces of attraction. Therefore, the boiling point for Cl2, Br2, they are generally low. Yeah. But again, okay, when it comes to Cl2, Br2 and I2, I want to actually look into comparison between the boiling point. Okay, which one will have the greatest boiling point? The one that is going to be greatest boiling point is the size. Yeah, you see, this is small, this is getting bigger, this is going to be way bigger. So if the size is more, it means why? Because it's the number of shell is more. Why you have number of shell which is more? It means more electron. Okay, if you have more electron, it means that more electron can be at one particular place. That is going to make the delta positive and delta negative to become more, more stronger. Okay, that's why, okay, if you look at boiling point for I2, it's going to be higher compared to Br2 and compared to Cl2. Why? Because, okay, it got to do with the size, with the electron, because the boiling point, even though it is affected by ID, the boiling point for I2 is greater because more electrons means it's going to form a more stronger ID. Okay, so this bond, okay, is also going to be known because it's related to electron. We call it as dispersion forces, and in your syllabus we call it as London dispersion forces of attraction. Okay, and with that, I finish today's revision. Okay, so I'll start recording.